So you're here for how OpenStack drives the Linux kernel to maintain storage. So I'm Mike Perez. I'm the project technical lead for the block storage project Cinder. Yes, that is a real tattoo, and I'm not ashamed of it. And I've been working on OpenStack since 2010. So that's all the way back to the bear release and back before block storage was still part of Nova Volume. So, and then eventually we forked out of Nova Volume and created another project called Cinder. Oh, and thanks to Datera, they take care of me for allowing me to work upstream. So my life consists of OpenStack and Cinder. And this roughly translates to almost 8,000 patches a year that we have to review. It's not just me. We have 353 reviewers, a very small core team. I'm trying to grow that. So if you're interested in contributing to OpenStack, we are a very nice team. So we're already integrated into core as well. So there's no graduating into core or anything like that. And but as you can see from the numbers here, specifically of the number of patches that we get, so 8,000 patches, and only a small percentage of those actually get accepted. And it's just because, unfortunately, not everything fits with our mission statement. So my goal is to actually provide some sort of interface for users to be able to use a virtual pool of storage. And for the typical user, they don't actually care that you're running vendor X or vendor Y. And the reason why is because the whole point of the cloud is to have resources readily available. Okay? The whole reason why we've done all this to begin with was we're trying to solve this problem that exists in IT environments now, where you have that guy in IT named Bill who has a thing for you, and you know it because he's always giving you trouble, and you want to be able to have some sort of persistent storage for your application. But you have to fill out some form, Bill takes his time, and maybe 2 weeks later you're already past your deadline, and you complain to your manager, but it's still your fault. So I want to solve that problem, and I also want to help IT as well by providing them resources, because still building a cloud involves some sort of human intervention. And so it's kind of a win-win. Developers get their resources. IT don't have to talk to developers. They could just make sure everything is stable and up. And the other thing that I want to do too is I want to provide an interface where exactly that experience, where the hardware doesn't, again, matter to the user. I want to provide a single interface where you could say, give me a 100 gig volume. It doesn't matter. And then I can attach it and start using it. So that mission statement turns into this. This is ugly, by the way. And I would expect everybody in the room to hate me if this still was a thing. And I can tell you today it is not a thing. So to your left, you can see the different drivers. And then each column is representing a feature. And each cell is representing whether or not that driver can actually support that feature at that starting release. So, and this is also really bad because every single driver has its own protocol, or it has multiple protocols. So if you're deciding to use vendor X with iSCSI, gotta look for it. If you want to use Fiber Channel, gotta look for that. This is a world of hurt. And again, this keeps going. This is another page of it. And it actually goes further on from that, but I think you get the point. So again, I would not be standing here today alive if operators really had to work this way. So the reason why I'm still alive, and my colleagues as well, is we nicely came into a room one day at one of the OpenStack summits. We have them every 6 months for the new release. And as I said, we came in nicely, and we were very friendly on what exactly we thought were the minimum features that defined block storage. I would be lying to you, though. It was not a friendly conversation. This was a grueling 2-day conversation, and in the end, we're still all friends, because obviously the project is still together. So in a lot of these, I just want to say what exactly is block storage and what kind of service, some sort of software-defined service, that's what people like to throw around. What does that mean? And to me, it's just the very, very basics. It's not really anything in terms of data replication or anything like that. I just want to provide a very, very simple interface. And the things that you could extend to that based on the drivers you're using, cool. I mean, if you want data replication, that's cool. I'm not going to consider it a core feature, though, because the core things to me is exactly what you would do with the service in terms of creating a volume, deleting a volume, attaching it, and using it. And there are other things like being able to create volumes off of images or cloning those volumes so you could do copy on writes. And along with that, extending a volume. Being able to have the volume from one size and then extending that out. I guess that's self-explanatory, but. So that grid, what happened? I like to think that the vendors got really excited and they want to OpenStack all the things. I don't blame them. It's a pretty hot thing. And the mass storage market of the 80s for all of the different standards that they have introduced to us, and now the problem that I have to work with. And in general, I feel like open source happened, which is still a beautiful thing, but everybody's coming in with their use cases. So, and when you're the one guy and for some reason nobody wants to talk to the community, they want to talk to just a person that they think can make the decisions. It's very overwhelming. You could get like I think I get 8 emails a day where I have to direct people to go talk to the mailing list or something like that. So before we start, I wanted to just go over some of the basics of just kind of distinguishing between what I'm trying to provide as service for people here and just also some general storage basics as well. So here, file level storage. We are not doing file level storage. There's a separate project in OpenStack called Manila. And it's really good at what it does. It forked off of Cinder. So, different vendors, they provide exposure to a share instead of a LUN. And it's a very different concept from block storage in the sense that there's coherency that goes on. It's a way different performance benefits or not benefits, but performance differences that you would get. The difference, you could do multiple writers instead of having a single writer that you would have with block storage. I'll go over that later, but in the sense, there's a variety of layers that you end up going through. And the protocol is usually just anything that's based off of sys. So different, not exactly what we're trying to do in Cinder. Object storage, other totally different use case. On the other side of some web service, you have some sort of file system that's exposed to you. It's balancing out that data in its own way. You're communicating to it through HTTP, and you're putting data with HTTP verbs. So put the data with the metadata for that data, and also getting that data through some sort of interface endpoint. There's a difference in terminology, where containers become directories and files become objects. And you might be familiar with this if you've worked with something like Amazon S3 or Swift. So now we get to block storage. So this is usually when you have just a couple, a variety of machines that are in some sort of, SAN-like solution. And what we really want to think about is we have just a bunch of, a pool of data, and we want to take a slice of that. And what we want to do with that becomes a block. It's just bytes. It's allocated to us in a multi-tenancy environment. And from there, I want to be able to export that, so then some sort of machine can use it, which we will call the initiator, and will actually consume it to attach it. It is exposed to it as a block device at that point. The problem with this, though, is that there is no coherency. So if you have multiple writers writing to this block that's been allocated to you, there is nothing that's going to prevent those from conflicting with each other. And you will end up with corrupted data, and you will be very sad. So that's the trade-off. You don't go through those multiple layers, so there's a great deal of performance benefit that you would get off a block device compared to a variety of other solutions. One thing to note here is that Cinder is in no way, shape, or form part of the data path. It is just the control path. Allocate me 100 gigs of a volume, get out of the way, and attach it to the VM, and the storage solution talks to the VM directly, or whatever is attaching it. And the other benefit I would say is the variety of protocols that you can use with this. I mean, you have iSCSI, you have ICER, and you have, what else did I list up there? Fiber channel and so on. A lot of these I don't even use, but we support them in there, and we have support for those different type of targets. So a little diagram. You have some sort of SAN solution. You have a LUN on there, so that's this allocated block that I was talking about. And you have this initiator. We'll say it's a web server. And it wants to go ahead and use that block that's in some remote location. So it does, in this case, we'll say we're doing iSCSI. It would do an iSCSI login. And this SAN solution would be exposing it somehow through a particular port, and it would give back based on some credentials that this web server has. Oh, you can use this LUN or this LUN or this LUN, and it's identified in some way for it to know which one it wants. It gets exposed as dev SDB on the web server, attaches it, consumes it. But only one web server can be using this. Okay. So the high level of Cinder. The great thing about this, and maybe you got this out of some other talks and from here for OpenStack, is once you pretty much learn how this is architected, you could pretty much move on to any OpenStack project. You don't even have to work in Cinder. You could pretty much take what I'm going to explain here and use it across any other thing that you're interested in. If you're interested in networking or Nova Compute, for example. So as you can see, in this particular interface, this whole mapping right here, we have the Cinder client, which is talking to the Cinder REST API, then to the scheduler, and then eventually to some sort of implementation of storage. And the client can communicate through the client or directly to the REST API, which the client would eventually do. So speaking on specifically on the Cinder client, of course it's written in Python. Just about all the OpenStack services are written in Python, or majority of them are. And like I said, interacts with the REST API. And you can use this client either through a command line interface or actually importing it into your own Python code. So this is an example of what the command line interface looks like. So I do a Cinder create, the name of my volume, and 100 gigs. Gives me back, okay, here you go, this is when it was created, and there's the name, it's in a status creating because we just did that, and it has no attachments yet. And then it gives you a variety of other information. But so that's the basics of that. And here's an example of using it in Python code. So I import in the Cinder client, and I go ahead and I instantiate a client object, and then inside of here, I pass in the username, the password, the project that this user is a part of, and an authentication URL that is usually given by your service provider that is running OpenStack. And then from there, we can go ahead and we can use that client object to create a volume. So we do Cinder volumes, create, and then the name of the volume and the size. That's it. You have 100 gigs. It will give back to you a way to actually export that so then it could become a block device on that machine that you're running. And to me, that's a beautiful thing. Like, I could be using a distributed file system behind this, and that's what I had to do to actually allocate something from it. And in my opinion, that's exactly how it should be. This is exactly the user experience that I want to give people. So, the Cinder REST API, CRUD operations for volumes, same with snapshots, same with backups. Also, for the admin users, they can manage the quotas. They can also move volumes from one backend to the other. So if you have like an LVM backend and you have some, enterprise storage that you're using and you want to move from the LVM backend, you could do that. And along with that, the extend volumes that we talked about earlier. And you can also transfer volumes to another user in the cloud. OK, so going back to my previous example with the Cinder client, something like this where we're, again, creating a volume called my volume. And with a size of 100 gigs, this could translate into JSON requests of the same thing, passing it a size 100, display name, my volume. You could do this yourself with some, like with curl or something, and you would get back this response. So pretty similar. So the Cinder scheduler, when something is actually coming in from the user through any of these interfaces, this is where the decision of which backend it's actually going to go to. So, I mean, previously you saw here that we have LVM and we have some vendor solution. So in this case, the user doesn't know this, but based on the volume allocation that they're doing, there is a set of requirements, and they're set by the admin user. And these requirements are usually based off of, in the sense that we did earlier with just Cinder create 1 or 100, that is whatever the default is that the admin has set that are those requirements that would come. So in that case, we could set requirements based off of, by default, we want to give the user this, like our cheapest option, so maybe some spinning disks. So by default, it will route to the LVM solution that maybe is just spinning disks and hardware. And then if we wanted to offer sort of tiering idea of solid state drives behind LVM, we can offer them a way to go ahead and set those requirements in their actual request. I'll go over how that happens, but for now, just know that the Cinder scheduler will take care of the routing. And then along with that, we get the reports back from each volume manager that is talking to some storage backend. And we know that it's still up. We know its capabilities, if it can handle those particular requests, those requirements that are coming in, and does it still have the capacity to take in more requests. So requirements, they come from tiering. This is a really small screenshot, unfortunately. But there is, trust me here, that there is something right here that says tier 1 and tier 2. So this is off of the dashboard. And you can actually specify from the Commandline Interface too to get the tiering that are available from the particular service provider through a Commandline Interface or the REST API, just the same. And then send along with your creation request of which tier that you want that they're offering. And then, so from here, the scheduler takes that as a hint of where it should send the request. And if it could actually take on the request, it'll give back an OK that it can do it. Otherwise, it'll say, nope, can't fulfill the request, and let the user know through the API. And the volume manager. So the manager is receiving in the requests from the scheduler that it has deemed that it can handle. And then so from there, this manager actually has the specific code to actually talk to the different storage backends. So this is where the vendors are actually providing in their drivers so that we know how to talk to them when we get a request for create a volume, create a snapshot, do a clone of a volume, and so on. And so these are just basically, we have a driver class, and then they implement that. And then the manager is going to call upon the driver that is loaded for it to talk to that particular backend. And then also use any sort of configuration options to know which IP and so on, information that it needs to talk to that driver. So, and again, the volume manager is typically mapped to one pool. So you would usually have multiple volume, if you wanted it on one machine, you can have multiple volume manager processes that are talking to their own backend, or you can have them on separate nodes if you want to satisfy some HA case. And you can also have these in an active passive mode as well, in case one of those managers goes down and it could take on the requests that come in case the one that was supposed to support a backend goes down. So in the backup manager, I don't usually talk about this one because it doesn't really get much love, but that's why I'm going to bring it up. It's a really interesting way of doing backups because I don't think it's the most efficient way. But what it allows you to do is go ahead and take the data that's off of that volume, as opposed to a snapshot where you're typically taking a snapshot of the entire volume. And what I mean by that is if you have a 100 gig volume and you're only using 10 gigs, you get the full 100 gigs snapshot. And that's really inefficient. But if, for a backup, we could just, take only what is actually written and back that up, compress it, put it into cold storage in some object store. And then whenever we want to restore again, we can do that. It'll be a little bit slow because, cold storage, cheaper disks, satisfies that case. So. Ideally, I would like to see something a little bit more efficient from each driver, maybe some interface that we can actually have exposed. Now, obviously, if you're using some sort of driver that offers their own object store, like Ceph, for example, which offers both an object layer that's built on top of, has the block layer built on top of that. So if you're doing any sort of backing up, it will efficiently handle the backups within that cluster instead of anything else involving Cinder in any way. So.
Is it only to the object store, or it can also put it to NFS store?
So there is no support for NFS at this time, or any sort of implementation of NFS. But what you can, so the current ones that are supported is there's one for IBM for their storewise, and then there's also Swift and Ceph, and I think that's pretty much it right now. So those are your three options. If any of the drivers want to support, adding in their object store, they're more than welcome to do that. I mean, we have the interface for it, but that's why I say I'm not too keen on this backup solution. It's really slow. I mean, if you think about it, you're chunking the data to an object store, and that could take some time. But you can also, have these happening in an automated fashion if you wanted to as well, and have them scheduled, so you ideally don't even know about it. Okay. So taking a step back. So you're all here probably to actually hear where does the Linux kernel actually get involved with all this. And I'm really, really sad because I don't have actual videos to show off a lot of the neat stuff that I wanted to show, but I still have some information to actually show. So the volume manager, right, is handling a lot of the heavy work here and understands how to talk to the driver and so on. From creating targets, though, as we were talking about before, the targets, I probably messed that up, but on the SANs, you probably saw that the LUN itself, that's the target. And the initiator wants to consume the storage resources from that target. So in managing the targets, though, you have to know specific information about the different fabrics that are involved. And if you could think about how that whole implementation would end up in Cinder itself, if I had to really know how to set up different packets to be able to communicate different fabrics and their hardware and so on, that could be really, really ugly. So I wanted to take, if you ever think about those infomercials that turn the whole screen black and white and it shows somebody doing something really impossible, that's pretty much what I'm going to show you here, and with the simplest case right here. And this is specifically using the hdreg header file from the kernel. And in specific, I just want to actually identify whatever the actual block device is that exists. And so to actually do this, you have to create a file descriptor of that particular block device. And then I know everybody in this room actually knows that hex 030D will actually get the identification information, right? No, you don't. Hopefully you don't. I don't even know that. Well, I know that now, but this will get the identification information from this particular, to the kernel, sending up an ioctl. An ioctl is a way for us to send some sort of, well, it stands for IO control, but it allows us to submit a request to the kernel based off of this command, which this hexadecimal is representing. And I go ahead and I create a buffer off of that to actually put the data in that I'm about to retrieve back from the kernel from fulfilling this request. And I can go ahead and use some byte mapping to actually get the particular data I want. And what do I get? That. And this is just the serial number and identification information and the model of the particular block device. And that was kind of ugly. But here's the problem, though. That particular code, just to get the identification information to begin working with targets, that was just a little bit. It gets even more complicated than that. But the problem here is that code that I just showed you with hdreg, that was only supported in Linux 2.6. It was deprecated in there, so unfortunately, we have to completely rewrite how the kernel does it now. So in order to do that, I have to begin defining in the specific SCSI header file of what exactly the struct looks like in there to send a SCSI command. And you can begin to see this is getting sort of ugly in the Python code. I don't recommend anybody doing this at all. If you're going to do any sort of ioctls, stick to C. But in my particular situation, I am writing Python code. I have a Python project, so I have to continue to work with this. So I have a SCSI command, and in there somewhere is the actual, the data struct that is actually representing the command itself. And in particular, I want to begin working with the particular hardware for whatever target that I want to work with. I have to, start somewhere. So let me start with ATA. So here's a header file, and I think this is right, and I don't really know for sure because I had to find some random document specification of what exactly the byte packet would look like. But it looks something like this. And in there is like sector count information, the command that I want to send, and so on, a lot of information that I wouldn't actually use to get the identification information of a particular block device I want to work with. But so I do it anyways to prove my point. So in here, I'm actually initializing the ATA command class that I just created, and I'm specifying specifically the command, it's hex 2e with ATA to actually get the identification information, and I want to send that as a SCSI command. So I send that ATA command object, and I pass that in to the SCSI header file class that I have set up, representing that struct, and I create a buffer, start and create the file descriptor, pass that along in the SCSI command, and same thing. But that was really ugly, and that was only for ATA. I still have to think about SAS. I have to think about other types of hardware that I want to support. I have to think about other fabrics I want to support as well. And that code is just going to get more and more ugly. On top of this, though, what makes this even the worst thing ever is that I'm not guaranteed with anything in the Linux kernel that those structs are going to stay the same. There's no compatibility guarantee that I'm going to have for my little user space program. So again, that was pretty much what I went over just a second ago. So I bring you the actual solution to this problem to be actually having compatibility between user space and the kernel. And that is LIO. And in this particular situation, I want compatibility when I want to talk to the kernel about storage. So the LIO stands for Linux I/O, is the target subsystem in the kernel. And it allows us to use this SCSI model of we have targets, we have initiators, and we have some sort of fabric that's completely irrelevant to us at this point. As long as we stick to the idea that there is an identifier that is representing the storage that we want to use, and some sort of module that the kernel already knows about of how to work with that particular fabric. And those details to me don't really matter. So in this case, I don't even have to use ioctls because LIO has support for something called configfs. And so configfs is a virtual file system. It's in memory. And so when I actually load up the LIO module, it will start providing a way for me to actually create kernel objects in this virtual file system. I'll go over that in a second. But so in a sense, with configfs, I can begin to create and actually destroy kernel objects from user space. And this is sort of similar to maybe something else that you guys might have heard of called sysfs, but totally different, and that it's just allows for creating and destroying. But I also want to be able to manage those as opposed to just those actions. So that's what configFS offers me in sort of a different way. But totally using sysfs for anything in user space, I don't recommend it either. So again, you probably really hate me from the previous examples of those, actually doing ioctls from Python. And I will repeat again that we should not actually implement those things since the kernel already provides it to us as long as there's a way for us to use it. And so an example of actually using configFS. So as one of the slides mentioned before, inside of the syskernel config, there will be a target directory. And inside of there, that's what's provided by LIO. And so there will also be different fabrics that LIO is supporting. So iSCSI is one of them. If I wanted to actually create a target inside of with iSCSI, all I have to do is a make dir and then how I want to represent that particular target. Typically, it's an IQN, so in that particular format. So I would do a make dir of that. And then if I do a tree on that directory, I get a bunch of files and directories inside of there. All of these files represent attributes to that target. And what's awesome about that is now I can have my user space program actually walk through that, and I know what the attributes are to this particular target. So what does that mean exactly? I have compatibility all the time. As long as whatever I'm exposing to whatever program that's actually reading this and wanting to do something with it, I know what the attributes are, and I could set them myself. Are there any questions on that? Okay. So, and then creating children objects within that, if I actually cd into that IQN directory, I can make a target portal group, and then that will actually allow me to, doing another tree will expose more attributes. So configFS is this actual, listing of files in here, but LIO is what's populating all of these files that are representing attributes. So again, the file itself is the attribute name, and the content in the file is the actual value. So if, for example, to make a little bit more of a case, that same iSCSI target that I was working on, I could just go into the target portal group, and I could do a make dir of an IP, and then it'll expose something like that. And believe it or not, that actually just now exposed this particular iSCSI target over that IP in that port. That's it. That's all I have to do. You don't even have to, you can have a user space program, obviously, that can just be reading off of these files and doing straight make dirs and editing the files directly, doing T, whatever you want. So I think that's a pretty awesome thing. And, oh yeah. So I didn't show you before, but it's like, what is it exposing exactly? So you could put a symbolic link inside of specifically like the lun directory, because in iSCSI, we expose luns. So in this case, I create a directory called lun0. And all this is to you is a file that is representing some sort of storage that I want to represent. So I just do a DD of, just some block that exists. We'll say it's like 100 gig, DD to a file. And in there, all I want to do is just expose that 100 gigs that somebody else can consume. So by doing this, of creating a symbolic link inside of the lun directory will be recognized by LIO to where it'll expose through that particular IP import. So where am I getting that at? If you were to do an iSCSI login to that IP import, you would then get back, oh, you can use this storage right here, and then attach it as a block device on your machine and start writing to it. So I had an actual video example of showing me doing the make dir and actually, doing a tree on the file and so on. So unfortunately, I can't actually show that. If anybody's actually really, really interested, I can show you from my laptop after this. So, and then RTSLib. So RTSLib is a Python module that we're using inside of Cinder today. And this is how this all hooks in. This allows us to drive the kernel today by using this interface that RTSLib provides to configFS and to LIO. And so we can use whatever RTSLib sees as fabrics. And fabrics are, the fabric modules, sorry, are the files that actually tell it what fabrics can be actually supported. And so you could think of there's an iSCSI fabric, there's a fiber channel fabric, and so on. And this is where that interface of how exactly that SCSI architecture model fits in with all this. Because all these fabrics really, when you break them down, again, it's just a set of features like discovery, authentication, and ACLs, and so on. It's broken down by some, and also exposing it over the network and so on. But besides that, there's always a worldwide name that's associated with that. In iSCSI, it's IQN. In fiber channel, it's just worldwide name. And that's where we set in these actual values in this particular fabric file. There's also a kernel module that is associated with every single fabric. So we can also tell LIO of which particular kernel module to use so that it knows what it's associated with. And this is what will actually create those different, like in the sysconfig file, inside of syskernel config target, there'll be a /iSCSI, there'll be also a /fiber channel, and so on. So, and this is what allows RTSLib to start using those. It makes the mapping based off of those kernel modules. So a little example of it, just to show how simple it is, creating a 2 gig file inside of my home directory looks something like this. I'm going to use the file IO subject object, and I'm going to use the file IO backstore, and I'm going to call it foo, and inside of there is a foo file that's 2 gigs. And then I'm going to use the fabric module iSCSI. I don't really have to know much besides that, except create a target called, just have a target that's based off of that fabric that I'm passing in. I create a target portal group, and then from there I could pass that on to a network portal, which by default is going to expose it over the public interface on that particular host that I'm running this on. And I want to associate storage with that. So I associate that same file IO backstore to it on LUN 0. Any questions with that? Cool. All right. So target CLI, man, this would have been an awesome demo. It's a really, really cool interactive way to actually be managing any sort of storage off of LIO. And so it's based right on top of RTSLib. So it just uses that library directly, and it allows you to actually go through the different tree and to create all these different kernel objects and children objects and in an interactive way. So you don't actually have to use code or anything. It's more for administrator purposes. But you can also do command pass-through as well, so you don't have to use it in an interactive mode. So, oh my gosh, it's sort of doing something. Cool. Well, it's doing something. So here, we're getting an ls of all of the different kernel objects. And inside of here, I go into the file IO directory, and I'm going to go ahead and create, based off of that home directory, that name of that file and the size of it to 2 gigs. I go back up to the parent, and I'm going to switch over to the iSCSI directory, and I'm just going to say create. And that creates a target portal group, which creates an IQN. And then from there, I go to the LUNs, I create a LUN, and I associate it with storage object foo. And I go to the network portal, and I do a create, which is, well, you can see 192.168 is now up there. So, wow, that was kind of lame. But trust me that that file is now exposed over over that particular IP and that port. So kind of a little example of how you could do that in an interactive way. So your takeaway for all this is that the lower level stuff is pretty cool, and it's also really complicated. And so I kind of believe from a higher level services that I want to make those things actually usable and in a more friendly way. And I kind of think that's exactly, just with that example of Cinder Create 1 and everything that goes on behind that, of actually allocating a volume and being able to create a target off of that, that's all really everything that it's going through, but from a much simpler interface. And you should never do ioctls in Python, because I hurt myself enough doing that. I will say that over and over. And I also find in general the configFS solution really beautiful, and I wish that more kernel modules would actually support it. So LIO is being one of them, and unfortunately everybody else accepts ioctls, and again, those can change. The different hexadecimals can change, the structs can change. So in my opinion, being able to read off of a virtual file system of exactly what the attributes are to those different objects that I'm creating in kernel space, that is better than me defining those attributes in the structs themselves in my own Python code. So, thank you.